Okay, hello everyone. It's 10 past the hour and we are starting. Today we will have Brian Bingham. Brian received his bachelor's degree from the Missouri University of Science and Technology and his master's and PhD degrees from MIT, all in mechanical engineering. He is currently an associate professor with the Department of Mechanical and Aerospace Engineering at the Naval Postgraduate School in Monterey, California. His research interests include the design, dynamics, and control of robotic systems. You may ask questions during the talk, either using the Q&A chat or raise your hand. That's it. All yours, Brian.
Thanks, Coral. Thank you to Coral and Chris and Nicole for setting this up. One little minor correction, the academics in the virtual room will appreciate this. I just found out yesterday that on July 1st, you won't have to call me associate professor anymore. So I'm very excited about that. Great to see some familiar names and faces in the Zoom room. And as Coral said, happy to take the discussion in whichever direction it goes. I put together a talk that just that really highlights the most recent stuff we've done in simulation, and we can go from there. Looks like Larry has his hand up. Oh no, it went down.
I was just applauding at your promotion.
Oh, thank you.
I'm still trying to figure out how to do that. You know, sorry.
I appreciate it. Yeah, thank you very much. So I'm going to share my screen and we'll take it from there. Let's see. I think this is the right one. So Coral, can you give me a?
Yeah, looks good.
Okay. All right. So so a few people on the call. A few people on the call have worked with me in the past and probably know more of my work in the more field experimentation into things, going to sea and putting robots in the water. Since joining the Naval Postgraduate School, and maybe a little bit ironically being a little more close to the Navy, we've gotten much more interested and much more involved in simulation work. And you know, I can say that I probably, in all honesty, was a little dismissive of simulation work back in the day, but I've come to, as the applications of what we do in underwater robotics have gotten more complicated and more expensive. And, you know, now you'll see some simulations today of aerial vehicles working with surface vehicles, working with underwater vehicles. Those experiments are really expensive and really hard to coordinate. You know, we can wait a year or two to get ship time. And so I will never say that simulation is a substitute for getting stuff in the water, but it does allow us some really great flexibility. Some of the stories that I like to tell are of doing student thesis work where we have had rules before where we will not, we do some little field work here with small unmanned surface vessels. And my agreement with the students is I will not book the pickup truck to take it out into the field until you show me that, being from Missouri, I can use that phrase, you show me that it's going to work in simulation. So you can see there with the slide, you know, it is really valuable for testing new ideas, for testing them in a variety of environmental conditions that may not be easy to find in the ocean. And we can do a lot of things that are all in support of being able to be more efficient with that valuable tank time, ship time, as we go through it. So on the right-hand side, you'll see, so this is a collaborative effort. We're working with folks at Open Robotics. So if folks are familiar with the robotics operating system or the gazebo simulation, through them, we've had the last couple of years had some great interns for the Google Summer of Code. If anybody's working on open source projects, that's a great resource that Google supports. Woods Hole Oceanographic, we're working on I won't talk too much about our project with NOP, and then the funders of this have been NOAA through NOP and through some of the stuff that CCOM works on, and ONR and DARPA. So I'm going to tell two parts of the story. I will endeavor to be done at 10 minutes before the hour, no later than, hopefully a little earlier, to leave time for questions. And then we'll definitely kind of take a hard break at the end of the hour, and I'm happy to stick around and talk. So part one is about things that happen at the surface primarily. And we got into this around 2017 with a program called Robot X, which I don't think University of New Hampshire has a team in yet, but this is an international student competition using unmanned surface vessels. So you can see there on the bottom left, there's a picture here of one of these vehicles called a wave adaptive modular vehicle. It's actually generated by a small company here in the Bay Area. It's pretty unique naval architecture design. They've got it in a bunch of different sizes. It makes for a great sort of pickup truck to put lots of sensors on and do stuff out in the ocean. So they have run that competition since 2014. They started in Singapore, then they moved to Hawaii, where I used to live, and they did 2 years there. And then so they had to skip 2020 because of the pandemic. And then 2022, they'll be in Sydney, Australia. And if you're familiar with like the DARPA Robotics Challenge or the Subterranean Challenge or some of the swarm challenges they do, a lot of these competitions have a virtual analog because it's a great sort of wide funnel to get teams involved, to both attract teams and then to have a sort of first sorting mechanism to see teams' capability. These robots aren't cheap, the sensors aren't cheap. So before ONR invests a lot of money in provisioning those robots and getting them to some place around the world, we can do a lot of things in simulation to test. And then a similar project called the Virtual Ocean Robots Challenge, or VORC, a bit of a clumsy acronym, that we had a team from the University of New Hampshire. So Val Schmidt and Roland Arsenal and Coral Moreno, our host here. I know of those three, and I'm sure other folks from UNH participated. And that used a monohull vessel shown here on the right, with a simulated version of La Spezia Harbor in Italy. And so I'll do a little bit of a deep dive, no pun intended, on a couple of the features of that. The big idea is that what we're trying to do, and our real sort of high level goal in this, I've been involved in maritime robotics for 20 years now, yeah, at least. And we want to try to start connecting some of the great things that are going on in the other domains of robotics to our maritime community. So one of the things that's going on is investment from lots of different folks, industry, academia, government, in tools. So probably a number of you have heard of the robotics operating system. I'm not going to talk too much about it, or the gazebo simulation environment, which is used by tons of folks. It's a very general purpose simulation. Brian Gerke, the CEO of Open Robotics, would call it the best possible substitute for the hardware robot. It consists of some underlying physics. You can simulate sensor feeds, so you can basically simulate what your algorithms will see and hear and feel in the real world. It has a graphical user interface. You can run it on the cloud. And what we added, the sort of MPS piece in blue, is working with Open Robotics, added some environmental pieces that are specific to the maritime environment. Some really simple hydrodynamics, some models of boats and sensors and buoys and docks, and then really, I think almost the most important thing is some of the specific underwater sensors. So I'll talk a little bit about some of the stuff we're doing with forward-looking sonar, getting into some of the things that would be more interested in the hydrographic survey, but it's really early. I've talked with some of the UNH folks on that front of it. But so the blue parts are what we're trying to add to it. And I'll talk a little bit about how we link that up. So these simulations, the capability is, like I said, to use Brian Gerke's words, we want to create the best possible substitute for the real robot. And we want to exercise the different parts of what we would sort of colloquially call the autonomy. And so in order to exercise the autonomy, we want the boat to move like the boat will move in the experiment. And so one of the parts that we have is, if you're familiar with like the Fossen unified vectorial model for robotic vehicles, this is what the same equation that's in every paper on underwater or surface vehicle dynamics, at least in the robotic side. So we implement that within this gazebo structure and make a lot of simplifications, because one of our constraints is we want it to run in real time. So if you're, this is not a naval architecture simulation. This isn't AGER or LAMP or Navisim or anything that's going to allow you to design the next DDG 1000 hull. But we can put a shape into this simulated ocean environment, and using these very sort of almost standard approaches for maneuvering, so operating in X, Y, and yaw, and sea keeping, so pitch, roll, and heave, we can generate motion that exercises our control system and exercises our perception system in a way that is similar to what we'll see when we put these vessels into an experimental endeavor. So that's the kind of the big idea behind getting some of the hydrodynamics, some of the environmental forcing into it. And one of the things that we bring into that is maybe a little bit different in what we've done in simulation versus some of the other stuff is we try to relate it back to oceanographic descriptions of the environment. So by that we mean we generate wave fields based on simplified, well-developed sea wave spectra. We in particular we use Brett Schneider spectra, which is we can talk about that decision if we want to, but it's an oversimplification. But we can then relate the sea state that's in simulation to a sea state that is from an engineering standard. There's different folks. Susan Bales has a nice way of sort of capturing, like, if we're at sea state 2, what that means in terms of the Brett Schneider 2-parameter Pearson-Moskowitz wave spectra. So we can relate a engineering spec to our testing back to the environment that we generate in simulation. So basically what this shows here is that Brett Schneider spectrum, we generate, there's 2 parameters to that. So we can generate a statistical description of the waves. And then from this statistical description, so this is period on the x-axis and or frequency, and then what effectively turns into wave energy here, we can generate for a particular sea state, we can generate over here on the left, you can see the 3-dimensional surface that is reflected both in the visual field and in the physics, which are slightly decoupled. The trade-off there is that from a purely aesthetic point of view, we could probably make it look better by faking it, right? And so, I won't even use any vendor names, but there you can go get a plugin for a game engine, and it'll generate ocean waves which look really good, but you can't necessarily relate those back to the oceanographic criteria that generated a similar wave field. So what we want to try to do is kind of bring it a little more into the engineering design side of it. And so then we have the wave field. We can use the vessel model I showed you before. This is kind of a picture. We discretize the hull, and then we generate based on the simulation typically runs at 1 kilohertz, so 1,000 times a second. It is sampling, okay, where's the wave field, where's the hull relative to that, calculating a bunch of discrete forces and applying those forces, and then the underlying well-vetted rigid body physics engine takes care of the rest. So we're just generating these external forces. If you see if I can click the right key to go back up one, the wind and the wave forces here in the right-hand side of the Fossen's equation. So at the end of the day, and I'll show you some videos of that, what we're trying to do is generate motion that is both qualitatively and quantitatively similar to what we expect in the experiment. And it allows us to run tests. So when we run these competitions or when we run our own tests for our own development, we can say we want to test in sea state 0, sea state 1, sea state 2, and sea state 3, and every sort of increment between. which is really good because it allows us to sort of explore that envelope and find out where things are going to break. So we do something similar. Again, I won't go through the math too much, but this is actually, we haven't even published this quite yet. We're putting this into a special issue this spring. We sort of generalize a standard spectra from the middle of the 20th century that describes the wind, and then we can do the same idea. We have a statistical description of the wind, and then we can make some simplifying assumptions and calculate that for a sort of case of sea surface roughnesses. We can calculate that function of frequency, the gusts in the wind as purely a function of average velocity. And then this graph up here is just supposed to show it's normalized on the top, but if you look at the bottom, you can see that for wind speeds at 1 meter per second or 2 knots, or 4 meters per second or 16 meters per second, we can generate these time histories. So this is detrended, so we're only seeing the sort of random part of the wind or the gusts that are part of the wind. But we can generate, again, we're not going to generate the exact conditions off of, you know, Hampton Beach, but we're going to generate conditions that are statistically similar to an average wind velocity, both in terms of the mean component and the variational components. So so those are kind of two of the, you know, I was talking about how we sort of extended the generic gazebo robotics engine towards the maritime world. We do a bunch of other sort of stuff, and then these videos will show sort of based on a couple of these tasks. So the one on the left is these were two of what we call the foundational tasks. So we want to be able to get to where these robots are doing very sophisticated things, but we have to be able to first do some pretty simple things like go to a position. And so over on the left is one of the teams that participated in VRX, which is the Virtual Robot X competition. And their team doesn't see any of this. This is all done autonomously, and, you know, basically our testing of their software. And they're given a position, like if you're familiar with dynamic positioning on larger ships, they want to do DP on this vessel and this catamaran in, there's no real optical component or surrogate for the wind, but you can see that the vessel is moving around in the waves. And so what they need to do is go to this position, which they have a GPS location for this position. They need to estimate their position, and then they need to achieve that XY position and heading. And then we test that in sort of simple conditions, like lake-like flat conditions. Then we test it where you've got a wind that's directly on the bow, and then we test it with a wind that's kind of coming off the quarter to be able to see where things break. This is the University of Florida's team, which has, you know, these are not, what's the euphemism there? These are not selected at random, right? This was the University of Florida, who's for a long time done a really good job. Their station keeping in this program has been sort of pretty notorious for being pretty good. And part of it is the mechanical design of the way they've got their thrusters oriented. Over on the left is the other part that this sort of physics exercises. So you can see one thing on the right is that we've added some fog to the environment, so you can't see as well. And then this is kind of an interest. So we wanted to isolate perception. And so in simulation, we want to be, you don't have to worry about controlling your robot for now. You just want to worry about perceiving obstacles. And so a nice thing about simulation is we can virtually lock the vessel in those maneuvering components in X, Y, and yaw, surge, sway, and yaw, and allow it to move in the sea-keeping components. So heave, pitch, and roll. And so what you see here is that the task was to report the identification and location of a known set of objects, in this case, like red and green buoys, black obstacles. Again, they don't see this third person view that you see in the window, but what they do have access to is the simulated camera feed. So if you look in that camera feed in the lower left corner of the video, you can see that one challenge of doing this that is different than a 2D indoor robot. On the ocean, your camera moves around. And so you want to be able to have your identification, characterization, localization of objects be robust to the camera moving. So again, exercising that piece of the perception in terms of being able to perform in a variety of environmental conditions. So the last sort of little bit about the surface vehicles. So we've done these 2 different competitions. We're actually gearing up for the next virtual competition, the Virtual Robot X competition that'll happen sort of starting any day now, and will lead up to probably run over the new year into the spring, and then lead on to the culminating physical event in Sydney, Australia. And I think UNH, I'm really have no vested interest. I don't think it's a conflict of interest, but I think UNH should have a team. And one carrot we can dangle there is the venue, the new venue in Sydney, Australia looks fantastic. It's actually they're from the Olympics, the whitewater course. So they won't turn on the pumps for the whitewater, but it's this beautiful basin on the west side of Sydney near the Blue Mountains. And the virtual part is that kind of wide area of the funnel to get teams interested before they invest the time and fundraising to actually field a robot. So, so I mentioned that the competition that UNH actually participated in was a intermediate competition that was done this fall, and the culminating piece of this was a simulation task where the teams were, this is all done completely autonomously, looking for a black box. So looking for an acoustic beacon. Again, in simulation, we can give a physical manifestation of that. It's this red marker in the middle. And so what this team, and I honestly can't remember which team this is, they have to navigate through the channel marked by red and green buoys. They have to avoid obstacles, and they're using a surrogate for a 4-element acoustic array to be able to locate that black box, which they're receiving acoustic signals for. So that's kind of, to show sort of how we can bring all that simulation together and be able to do stuff that's similar to what we would want to be able to do in the real world. Again, this is all in preparation for doing physical experiments. Doing things in simulation is never a surrogate. You're never gonna be able to take that algorithm for recognizing red and green buoys and take it straight from the simulation to the field and have it work perfectly. But you can certainly get 90% of the way there, let's say, in simulation. And those of you who've worked in the field before have, at least I'll say it this way, I have experienced like finding bugs in my C++ code that I certainly should have found in the lab well before we were paying $20,000 a day for a ship. And so we want to get rid of all of those issues so that the things we're testing in the field are things that we need the field to test. And so one more way of saying this is, if it works in simulation, it might work in the real world, but if it's broken in simulation, it definitely won't work in the real world. So just a couple of sort of ways to think about why we're doing this simulation stuff. So the last thing, actually the last thing I'll talk about, which is kind of getting to the multi-domain part of it. So this simulation is, one of the fun things about it is we've started to see a lot of different uses for it. And what you see here is a commercial company down in the Boston area that is working on a launch and recovery system for an unmanned aerial vehicle off of an unmanned surface vehicle. So if you can see here towards the bow, there's a quadcopter. In the stern is a bright yellow industrial arm. And the concept here is in simulation, we are learning to fly the UAV to the arm. The arm does the heave compensation to allow it to dock. And then we can launch and recover in a much higher sea state, these unmanned aerial vehicles. So one of the nice parts about bringing together these tools from the greater robotics community is there's really good support for things like flying drones around. All right, I'm going to take a break before I talk about the underwater pieces of it. So we're 34 minutes in. So I'll maybe just pause there and ask if there's any questions on the surface craft parts of it. It doesn't have to be. I can talk about underwater vehicles if that's where we want to go. Hi, Val.
Hi, Brian. This is Val. I have a question. I have a lot of questions, actually.
Yeah, we should probably talk. Yeah,
I'll keep them brief because I'm sure other people have questions too. But I had a couple of quick ones. Have you talked with the Open Robotics folks at all about modifying the gazebo simulation to better support field robotics? Things like coordinate system changes and simulations that extend over a large aerial extent that have big changes and big differences in scale, or maybe a big extent in horizontal scale and a relatively small extent in the vertical scale.
Yeah. So I'm gonna skip forward. So let's see. So that is.
Sorry, I'm stealing your fire, aren't I?
No, that's all right. So no, that's great. So this is definitely like things that CCOM would be interested in, and I know we've talked to. So there's a lot of people talking about those kinds of issues, right? And folks at Woods Hole Oceanographic, folks. So I think Embari is doing a new project. It's yet to be determined how much of those features are going to be integrated into Gazebo or the next generation of Gazebo, which is called Ignition.
Yes.
So this is stuff that really a lot of it came from Mike Chikuba at Woods Hole Oceanographic. And we have a postdoc here that sort of moved it into some of the stuff we're doing. And the basic idea is, as Val mentioned, is that Gazebo was really conceived for small spatial areas. And if you imagine, the default is that for every object, everything in the environment, it is all the time looking for the cross correlation of contacts, right? So is any element in contact with anything else? And that explodes exponentially with spatial scale if you leave things at the same resolution. So one of the kind of ways around this that has been developed both by Open Robotics and with Woods Hole's bathymetry processing. Open Robotics done it more for their subterranean challenge. Tim Chung's at DARPA's challenge for doing underground robotics, again, large areas, is to use kind of tiling. And so we're gonna only load, if you've got a big bathymetry map, that's what this shows here, is we're loading bathymetry from NOAA. And so we pre-process the bathymetry into stuff Gazebo can understand, and then we only sort of load into the simulation the immediate area around the objects of interest, and then we unload them when they go away, so that we don't have to worry about, like, we're pretty confident our AUV is not going to, if we're operating in New Hampshire, is not going to crash into a seamount off the West Coast. So we don't need to have that part of the map in memory. So yeah, so that's kind of coming, right? Yeah. So yes, I think there is interest in that. But as we've talked about, I think one of the things that I'll talk in as we get through the slides is it's a community, right? This is all open source stuff, and I think that one of the reasons I wanted to give the talk is just advocate for UNH giving back, right? So you guys have got some great capabilities and some great tools, and if we, it takes a little extra 10%, but as we solve some of these issues, to share them broadly.
Thanks, Brian.
Yeah.
We have one more question from Diane. Brian, this is really exciting. How well does the summation of the stress work? Which of the stress estimates is the best, and which is the one that needs the most work? As I recall, Brad Schneider breaks down in shallow water.
Oh yeah, definitely. Okay, yeah. So
And you're not sharing the screen anymore.
yeah, I couldn't figure out how to look at the chat. First, hi Diane, good to hear from you. Let's see, I'm gonna get back to, I think that's it. So It is somewhat generalized in that, so the question was, if we're generating, I think, part of the question anyway, was if we're generating C states and we're generating C states based on a particular spectrum, how general is that? So, or how do we use other spectra? And the formulation. Oh, go ahead, Dan.
Brian, to comment on that, I guess what I'm thinking is that in shallow water, the nonlinearities get large and the sea slope gets steep, and it's both skewed and asymmetric. So, and I think the Brettschneider is certainly appropriate as a way to start, but do you have thoughts on where to go from there?
Yeah, so yes, we just haven't had a demand for it quite yet. But we talked about, like, right now we're using kind of we can simulate the steepness of waves using I may even be saying it right, Gerstner waves. But we talked about there's a colleague of mine from Carter Rock, Joe Clamo. He's always given me a hard time about we're making it too simple, but certainly for getting some of the using like Stokes waves to get a little more reality into the actual wave shape. I think the lowest hanging fruit is to generate more complex wave spectra that have more than just two parameters. I mean, we're kind of treading this line between complexity and the users just want to have one dial that they turn for C state. So in terms of generating if you can generate any sort of C spectra, even if it's not continuous, we can discretize that and generate a wave field from it, but we're still limited in terms of that wave field shape is still not sinusoidal. We can generate steepness. There's a Q factor in the Gerstner waves, but it's pretty limited. So again, I think that's where we're at with it. I think it's totally possible in this kind of overall framework to do that if there was a need.
Thank you.
All right, I'm gonna go to part two because there's some UNH specific stuff there as well into autonomous underwater vehicles. So this part of the story, which I'll do in 8 minutes, is has to do, the two kind of use cases are one with Woods Hole Oceanographic and the NOT program. They're developing down here in the lower right with Teledyne Web Research a hybrid underwater glider. So it is a similar to a standard Slocum glider, except it's got a couple of motors on the back. And they're using that for doing long duration bathymetry mapping. So right now they've integrated a DVL. They're going to integrate a kind of, by UNH standards, a very low resolution bathymetry, and using the underwater glider with probably folks are familiar with the Wave glider. I now think owned by Boeing. So using the Wave glider as the navigation and comms gateway for an underwater glider. That's the sort of genesis of that project that's been going for a couple of years. COVID has slowed it down a bit. It's known as Epic Dog. And so they want to be able to do the same thing before they go off Puerto Rico and do the real deal. They want to test their terrain-aided navigation, their inverted USBL navigation, and this new vehicle in a simulation environment. The other project, which is a sponsored project, but they have an onerous public disclosure. So we're not going to talk too much about the actual use case, but they want to be able to do long endurance mobile manipulation. So vehicles that are underwater for months, traveling kilometers, and manipulating things on the seafloor. And so we want to, again, be able to provide both the government and the performers with a surrogate environment to be able to do that. So now we get into, a very different sort of physical domain. We're not as concerned with waves. We are concerned with ocean currents. We're concerned with the same sort of dynamic equations, but in 3 dimensions, or in six degrees of freedom. and a bunch of the manipulation. So I'm talking about sort of robotic manipulator arms, and I'll show you some sort of videos of that. So we've been able to create a bunch of surrogate vehicles. So, you know, generalizing commercial off-the-shelf vehicles into artistic renderings and hydrodynamically similar vehicles. That's been kind of an interesting odyssey, because obviously the vendors get pretty proprietary when you talk about the details of their model, but we just want something that operates kind of similar to standard remotely operated or autonomous vehicles. So we've been able to generate sort of a new library of vehicles. I'll show you some other ones in a second. We've been able to generate some surrogates for, they don't look very good yet, but they operate the same. They have the same interface as the some of the standard electrical and electrical hydraulic manipulator arms. Sensor models. So this is actually something that our postdoc here at MPS, he's not actually physically here. He's still in Korea because of COVID, and Derek Olson in the oceanography department, we've been really interested in, and you know, we've been learning some stuff from Val and his team about simulating underwater not near field, but short range forward looking sonar. So this is a big part of the perception for underwater manipulation in turbid environments. And this was something we saw that we could contribute to. So, so this was just released in December, and we're able to, the sum of this is we've got, which is kind of new to Gazebo, a physics-based method using scattering to generate not only like up here in the upper area, what had preceded and what was out there before was really very much image-based. So trying to generate images that look like the post-processed version of what a sonar would give you. And what we're trying to do is generate something that a machine could look at. So actually looking at not the raw data in the sense of individual acoustic channels, but looking at the post beamformed intensity as a function of beam range or beam time. And so that's kind of cartoonish here of generating those intensities, add in, you know, different kinds of noise, and we can, we're actually working with Laura Lindsay and Aaron Marbo at University of Washington APL. They're doing some tank tests for us. We were trying to do those last year, but the pandemic got in the way. Trying to do some tank tests to be able to tune the model and do some simple verification of the underlying theory. So so that generates kind of, there's a little animation here, so you can start to put your sonar into a virtual tank and get things that not only look like sonar images, but give you the same data interface. And actually, you can take this. One thing that I, you know, probably be picking y'all's brain about it is, you know, we would like to find a, maybe not open, but the least proprietary sonar viewer out there. So we've tried to reverse engineer some of the BlueView SDK, some of the other commercial viewers out there, but we would really be interested in being able to, you know, have our data plumbed into an honest to goodness sonar viewer. So I'm going to kind of accelerate here because I want to talk about the UNH pieces. But Dana Yerger, a long time ago, when I can remember when we didn't always use Doppler velocity logs, and this is obviously even the reference is dated, but you know, he dubbed the Doppler velocity log the American Express of sensors. You don't leave home without it, and the Doppler velocity log is, you know, sort of become almost a meme in underwater work in our simulation work, in that, you know, there is like 14 different implementations of a Doppler velocity log in simulation, and we're trying to bring those together and bring together some common messages so that we're not all reinventing that wheel. And underwater LiDAR, skip over that a little bit. So I mentioned the being able to do tiling and bathymetry. But the real story, I'm going to skip the flying lead piece. The real story that I kind of wanted to tell is some of the stuff we've done in collaboration with CCOM and through the National Oceanographic and Atmospheric Association and the Global Foundation for Ocean Exploration. So one of the ways, this is a bit of a C story, so to speak, is that we've been able to use this. So, gosh, this was, I think, 2016. We started using these simulation environments. So over here on the left, you can see while the mechanical and electrical team were building out a new remotely operated vehicle called Yogi, those of us who were interested in the control side and writing the software for that vehicle, this is not even an exaggeration. I was writing the control software with a simulation at my kitchen table in Pacific Grove, California, while the folks in Rhode Island were doing the hard work of assembling the foam pack and getting all the thrusters to work. And then we were able to come to the tank there in Durham in the wintertime, of course, because that's when you go from California to New Hampshire. And we were able to put that vehicle. This was, we've got a long, the Dave Lavolvo and the group there has a great relationship with y'all at CCOM and have tested many vehicles. And we were able to come there for a week. I think it must have been early 2017, and put the vehicle in the water. So you can see this kind of from simulation, which doesn't look very good, but behaved this very, very similarly. And it was one of, at least for me, the success stories of being able to write all the software architecture in a simulation environment. And then I think there may be people that can correct me on the call, but I think during the first day, we were able to get our closed loop control so that we could hover, station keep, move predictably in X, Y, and yaw of this vehicle in the test tank at UNH. Which made it a lot more productive tank time. And so that simulation, I know this is hard to see, but it actually, I don't know, to those of you who are into it, it gets pretty interesting because we have a bunch of different pieces and parts. We have the yellow pieces, which are actually in Ross and Gazebo. For that system, we still use, most of the work is done internally with LCM, which is the lightweight control, communications and marshaling, which is another middleware, and we write bridges between the two. So basically with the simulation, we can generate Doppler velocity log, fins, compass, depth, we can develop our estimation algorithms, we can develop our navigation and control algorithms, we can even do the thruster allocation and sort of get these parts of the vehicle software going before, in parallel with the mechanical and electrical folks. And this is when this is one of the pictures I like to show our introductory feedback control, because this is Josh Carlson is a colleague, and he is introducing a disturbance into the vehicle. So the vehicle's trying to hold station, and he's using a boat hook to physically push on it. And as you push on it, the vehicle spins up and pushes back. So he's got a funny grin on his face there as he's acting as the disturbance to try to test our control systems. And we are in the process right now. Oh, sorry, I should finish my Yogi story. So from the tank at UNH, the vehicle got on a truck and went out to Yellowstone National Park, and with working with Rob Reeve-Sohn and his group at Woods Hole Oceanographic, looking at the geophysics of Yellowstone Lake, which is a beautiful place to work. Dave Lavolvo has been working there for 30 years. A new research vessel called Annie. This is that new vehicle with the control system developed in simulation. And then finally going out, I thought I put a picture of it in the water. I guess I didn't. Finally going out in Yellowstone Lake and doing real science. And then what we're up to right now with that team is this vehicle, which is much, much bigger than Yogi, has actually been in the test tank at UNH even before that, probably 3 years before that, probably 2012, 2013. And we are actively doing a refit of that vehicle that you see on the left there called Deep Discoverer, or D2, to its friends and family. And we have been working just this week on a digital surrogate of that vehicle. And so there you can see the little animation there of D2. And what we're working on now is refactoring the whole control system and new thrusters, a bunch of new components, a bunch of new capabilities for that system. And we're doing the same thing. We're taking care of all the stuff that we can, all of the software architecture, getting basically the plumbing of all the software working in this simulation environment. And then the next step will be to, I think in April, the end of next month, beginning of May, the team's gonna hopefully, I think last I heard, go to take this 9-foot tall behemoth into the tank at UNH, and then we'll start testing. And hopefully that testing will be much more efficient because we're able to do all that architecture work in simulation. And then, you know, as I said before, the stuff we're testing in the tank is stuff that we must have the tank to test, right? So so that's kind of the where we're at with that. I think that probably the second to last thing I'll say is, you know, there's tons of opportunity to get involved. Roland and Val and Carell have seen this. We had a community meeting that was very much grassroots in December of last year with the folks you see represented there on the right, and just to raise awareness about what everybody's doing, so that lots of times, you know, what the science or the engineering we're trying to do, you know, we're in a rare spot where we're actually interested in the simulation itself, but the simulation is always a means to an end. And if we can work together to develop these simulators to test out the new ASV at UNH, to test out the new vehicle for GFOE, we can get to the end state much quicker. So, aspirationally this quarter, I want to convene another meeting of the usual suspects. So if you're interested, drop me a line. So only a few minutes left, but you know, it is a team effort. We're lucky to be supported by great folks at NOAA and ONR and DARPA, and wonderful to work with folks here in Mountain View at Open Robotics and up in Woods Hole on the Cape. So I think that's, yeah, any questions? I'm going to turn my screen share off. So. Yeah, Ben, sorry, thanks, Roland. I was blanking on the name. Let's see. So the question are, stay current with our latest work, should we already be looking forward to technology like ROS2 and ignition? So for those of you who aren't in that world, so there's kind of a hard change coming down the road with these tools that the general robotics community uses. So there's ROS1 and Gazebo, which are the middleware and the ecosystem for doing robotics things in not just in the maritime environment, and Gazebo, the simulation environment, which are separate projects all within Open Robotics. Both of those are going through a huge change in architecture to ROS2, which is got some huge advantages, and Ignition, which has some really exciting things, as Val was mentioning, that to be able to scale it up, to be able to use different physics engines. I'll say a few things on that. One, I know that I went to a talk, gosh, pre-COVID up the road here at Moss Landing in Mbari, and the official party line from Open Robotics was, if you're new to developing with these tools, don't worry about learning ROS1, learn ROS2 and Ignition. My experience has been that they are quite different. We have, for our work, relied very, very heavily on the UUV simulator, so on previous work, and we've been talking about trying to find sponsorship to make that jump over to ROS2 and Ignition, but we would have to carry not only our work, but a bunch of the underlying foundation over to that new development environment. And we haven't bit the bullet on that yet. I know other entities are looking at that. I just got an email today from some folks in Brazil that were interested in moving some of that infrastructure over to Ignition. But one of the things I've found with this simulation work is that everybody wants to use it and nobody wants to pay for it. So you know, so that's it. And the last thing I'll say about ROS2, if anybody's interested, if anybody's tracking the Navy is coming out with, it has been for some time, the Unmanned Maritime Unmanned UMAA, Unmanned Maritime Autonomy Architecture. And this is envisioned as being the real commercial standard for how these different parts of a system talk to each other, so that the government can buy a platform from Boeing and an autonomy engine from a small company and a sensor from, you know, Teledyne, and they will all talk the same language, this UMAA. At first level, that should be compatible with ROS 2, but we've actually got a white paper coming out that there are some subtle differences, and it's yet to be determined if UMAA is going to be flexible or ROS 2 is going to be flexible. So, so that's if anybody's tracking UMAA or UMA. Professor Mayer is curious about what graphics engine they might. So the graphics engine is another, you know, it is not, and by the Open Robotics admission, it is not a, what do they call them, AAA game engine, right? It's there have been what I would say is sort of ad hoc instances of folks putting together some really great stuff in things like Unity and Unreal, the game engines that look really slick, like, you know, very much closer to photorealism. The Gazebo uses Ogre, OGRE, for the rendering pipeline. I'm not sure if Ignition, I think Ignition will have a significant more flexibility in terms of what graphics engine it uses. There's also the physics engine, and it uses, there's a few different physics engines you can use. The default is Bullet, which is a very well vetted, sort of well described physics engine. All right, so I promised Coral that I would, I'm happy to hang around and talk to folks. You know, like I said, good to see some familiar faces and meet some new people, but I want to give folks maybe take a breath and give folks the opportunity to take off if they've got an engagement at 4 o'clock East Coast time.
Great, that was so wonderful. Thank you, Dr. Bingham. Carl's having some technical issues, so I'm taking over for the rest of this. If anyone has any more questions, you can feel free to, you know, continue typing it into the chat, or you can directly ask yourself and unmute yourself. Otherwise, thank you again so much, Dr. Bingham. That was a really exciting talk.
Brian, can I launch another one at you?
Of course.
Yeah, I just wanted to comment briefly, like participating in VORC for us was like a game changer, because we knew we always wanted to get into the simulation end of things and just were pulled too many different directions and hadn't had the time to invest in it. And of course we made the time with the challenge. So it was great. And for the first time, I think Roland kind of mentioned this, but we have our own boat in simulation, and we're in the process of acquiring another boat, which we'll put in simulation as well, and make those models available to the larger community. So that'll be helpful.
That's fantastic.
I was curious in one detail about the simulation in the Fuston model that's built in there. Is added mass included in that model?
Added mass is included. It is and also in the underwater vehicle models. It is not guaranteed stable, so you can get into you can cause problems. You know, we've been able to. So yes, I guess the short answer is yes, it's included. You have to be a little careful if it, you know, if the parameter with the parameters you use, and sort of check that things don't go wrong. But we've found that for the purposes of developing autonomy, we can, you know, we just need something that moves basically like the boat in the appropriate sea state, right? You know, that we can be pretty flexible on the, you know, the fidelity of that naval architecture model.
Okay. I have a follow-up question to that. And if somebody like me, who's a programmer and not an expert in boats, wants to figure out the parameters that we need to use to make our boat act
I knew you were going to ask that.
realistic enough, how do I do that?
Wow, that is a great question. So, and I have not found a good answer for it. And I have asked other people that I know and there's probably people at UNH that maybe would have a better answer. I haven't found a cheap and effective way. Like, you can use like strip theory and come up with some, you know, you can look at like Newman's book and come up with some reasonable numbers. I can send you some stuff, Roland. I recently kind of did a little bit of a deep dive of like, how could I just do this just based on, just a rudimentary description of the hull shape, even if I don't have a 3-dimensional model of it. The naval architects, at least they have told me that even, so now you could put it into one of these naval architecture programs. Like, even I was surprised to find out lots of them are still for the maneuvering components are still coefficient based. So that, I almost feel like it's like sometimes the only way to do it is to do some like pretty hardcore CFD or build a model and put it in a tow tank. But I don't know. There's probably people on this call who know much better about how to get reasonable coefficients. Like, given a picture of my boat, can you tell me roughly what those coefficients are?
I mean, as an amusing anecdote, I took the WAM-V coefficients and put it with a model of our Ben, and it makes Ben drift like crazy. Like, it's like playing Asteroid.
Oh, wow.
It's fun, but it's not realistic.
Right.
Hi, Ben. I got a question for you, kind of in regards to things that work in the simulation but don't work in real life. How perfect is the data that's being generated for the simulated sensors and video, like in terms of timing? Is there a way to introduce kind of timing errors and latency into things? Because, one issue we were trying to line up and stabilize video footage using data from the Ben's IMU, and unless you exactly know when that screenshot, when that video shot was taken, it's very difficult to line that exactly up with IMU to kind of stabilize where that video is. And I kind of worry that when you use a simulation to generate all of your test data, that everything's just so perfect that your algorithm works, but then when you go in the real world and there's little things that are off or a little bit of noise, you can kind of have it fail.
Yeah. So I'll quote Dana Yerger on this one as well. He said most of the simulations out there are doomed to succeed, and that we definitely want to avoid that. So there are really good ways of simulating the communication network as well, and there are again, like every one of these pieces has its own sort of community and an own field. And if you're not careful, you can go down the naval architecture rat hole, or you can go down the communications hole. And so I'll just tell you a couple of things that I know about in that domain. One is, I think 3 things. One is the original project for Gazebo was the DARPA Robotics Challenge. And that was a semi-autonomous vehicle where you had a computer on the robot, a computer back at the home station, and they actually through in the cloud by running different computers, and using VPN tunnels, they simulated both the bandwidth limitations between those different parts of the system and latency and lags. So that's one sort of use case. They're also doing something similar with the subterranean challenge right now, is because you've got, you're doing like large distributed systems through, imagine like caves and tunnels. And so how do we simulate the Wi-Fi coverage in a tunnel, right? And that, if you do that from first principles RF physics, it's like it's the equivalent of doing CFD. So they've got ad hoc models based on the linearity of the channel, and this you can, they're very much, again, just ad hoc models on Wi-Fi connectivity so that you can test what happens when your system starts to break connectivity. So that's another use case. And then the last one, there's a woman actually here at NPS, Preetha Thusalaman, who has done some work on simulating using network simulators like, oh gosh, what is, it's not NC3, I think, NS3. So you can get like dedicated simulators that do like, both, like fiber, copper, or Wi-Fi network, so you can actually simulate those lags. But again, it's sort of like, all these different levels of fidelity and how much fidelity you really need to test your system. So, but you can integrate all of those into this. I mean, takes work, but yeah.
All right, thanks.
Hello, Brian. I'm May Wynn. We haven't met before, but I know you by reputation and through Tony Arnold.
Oh, no way.
Yeah. I also work in controls, and I feel a little bit ignorant in talking about this because my students deal more with Gazebo and ROS than I do. They reverted back to ROS 1 because ROS 2 didn't have as much support, and they're just waiting for the hump. So that's my first question. When do you think that will kick in? Second of all, my grad students have been working more through the simulation environment through UAVs. We're slowly working to the ASVs and the UUVs, but coordinating that, especially with implementing observer-based control, I'm still not convinced that, especially involving NARMAX, et cetera, I'm still not sure if we can do everything. What do you think?
Well, let me take the first one. I'm not going to have necessarily very satisfying answers to either of those. Like, when's the hump going to come with ROS 2 and ignition? I'm waiting for it too. You know, I think if almost like kind of as I described before, if you're developing like purely from the ground up, then I think ROS 2 and ignition are there. And this is just my opinion. Then ROS 2 and ignition are there. Like if you're going to develop everything yourself. But if you're going to use, which, you know, I think part of the promise of, you know, of getting on the same page with some of these things is that you don't have to reinvent the wheel. And if, you know, as a researcher, if you want your students to like, hey, I just want to be able to fly a drone around in simulation today, right? You're going to use a bunch of community supported packages. And I've seen that there's still, you know, I don't know what it's like I don't know, you ever see those like cross-country ski races where, you know, everybody's waiting for the other person to take the lead so they can draft, right? Like, I think we're still kind of in that realm. I do think it's coming. I think it's coming faster than I thought it was, but I think for graduate students whose main job is to graduate, like, you know, I think we'll know when the times come, you know, when I wouldn't upgrade until there's like a killer feature you need, right? That you just can't do your work anymore with ROS 1 or with Gazebo. And then, you know, but we're not there yet. Okay. So I guess like your other question, you'll have to maybe give me a little bit of clarification of what you're trying to do with the.
Well, okay, so I have different students trying different things. Well, let's take the UAV side. Okay. They're mostly working with Pixhawk based platforms. And it's basically you choose what's available instead of being able to put in your own, especially when you're dealing with nonlinear controls.
Okay. Yeah. All right. I think I'm tracking now. Like, you know, and we've just been talking about this because I think I can say this without disclosing anything. The Australian version of the Robot X, all they know so far is they want to have a UAV involved. And so, you know, a UAV working with a boat. And so we were kind of looking at, you know, we're talking with Open Robotics, and the PX4, like MavROS, MavLink stuff is pretty, my understanding is pretty well supported. Mm-hmm. But if you want to, it sounds like what you want to do is replace in some way and replace at least part of the functionality of the flight controller.
Right.
Right. Yeah. So, I mean, you know, I haven't had experience with that, but that's, you know, for the maritime world, we don't, you know, there are some people who use Pixhawks and things like that for controlling boats and underwater vehicles, but usually we're writing our own controllers. Okay. And I would be interested in sort of learning more about it because it's very much like it's very much a hunch at this point. I think in simulation, you can determine what type of control or estimation you need, but you're still, I know that you're not going to be able to tune it in simulation.
Right.
So, you know, so like to use the control example, like can I do pretty well with PID, or do I need model predictive control? I mean, like how much complexity do I need to put into the controller type to get performance? I think you can answer that with simulation. Does that make sense?
Okay. Yeah, that is. It's just that like, well, we're working with a lot smaller ROVs than you are. Like the Blue Robotics is based on P4. So if my UAVs are based on P4, my ASVs, if I'm transitioned to P4, I'm already working with ROVs that are based on P4. If I can integrate them all together, that would be awesome.
Yeah. I'd have to, I haven't used the Pixhawk stuff within simulation. I mean, we're actually for the project I showed where we've got a robotic arm with a UAV with a boat. We were just talking about that this morning, and I'm still learning how to fly drones in simulation. So,
Okay.
because it brings in a lot of different layers. You've got the simulation of the flight controller. It's I don't know. It's still. So I can't really comment intelligently on it. I know people have done a lot of things with it, but I personally don't have that experience.
Okay, all right. I mean, for myself, I'm playing catch up and I'm living vicariously through my students. So I'm trying to ask questions they would ask.
Right. So the best thing that you can teach your students is how to ask questions on the forums. If they will ask questions to where it is, they this kind of rubric, like, it should take more time to ask the question to answer it. If they're not putting, like, I have to counsel my students who are 30-year-old naval officers, like, don't just put up there, it doesn't work, help. Like, here's what I did, here's the minimum example, so that somebody can, because it does have a great community, but they will 100% ignore something where it's going to take a bunch of time to answer. But if they can ask it in a way that somebody can help them, there's tons of people out there that want to help.
Okay, all right. Well, I won't usurp the conversation, but if you don't mind, I'd like to ping you later on.
Of course, yeah.
Okay.
Yeah, I think there's a couple Brian Binghams out there, but I'm the only one at NPS.
Okay, all right, thank you.
And Tony knows how to find me.
Yes, okay.
All right.
Bye.
We have a question from Marcos Ferreira asking, how has your experience been with using ROS bridges to cross the chasm to ROS2?
My experience is pretty limited, but it seems to work pretty well. I haven't had any. I mean, the nice thing, talking UAVs, the nice thing about working underwater is things happen pretty slow. So we can run our control loops at 10 hertz and be fine. So I haven't, it's at some point the bridges and the transformations, stack up and you end up with latency issues, as we were talking about. But I have had, for the stuff that we've done in ROS2, like it's worked, really well. We haven't had any issues, and I think it's pretty well supported. The ROS2 is a different beast, though. It is very different, and like depending upon which underlying implementation of DDS you use, I will say that I was really excited about the idea of abstracting away the middleware, the actual way that the communication happens, but I have found in at least the early versions, I haven't used ROS2 in a few months now, but that you still had to understand the DDS implementation and the limitations of it. It wasn't a black box.
Thank you. Are there any more questions?
Yeah, Brian, I have one question about the drone and the arm. Do you want to bring the drone to the arm using like more traditional type of control, or like the learning or through?
Oh no, totally traditional, like like we were talking about, like using Pixhawk, Mavlink, Mavros kind of stuff to just give it a waypoint. Like we have a RTK GPS receiver on the end effector and an RTK GPS receiver on the drone, and a little motion capture system. And so we, it's like literally giving it waypoints and velocity commands.
Okay.
Great. Larry, do you have a question?
Yeah. Larry? No?
No, I'm fine.
Oh, okay. Sorry, I thought your hand went up.
Except to thank Brian for a really fantastic seminar. It really was inspiring. Really appreciate it.
Yes, thank you so much, Dr. Bingham.
Yeah, thank you all. Yeah,
probably would be boring to others. So if you want to stick around after the seminar, if you don't mind.
Yeah, happy to. All right.
Okay.
Thanks, Coral, Nicole, Chris, for putting it together. Yeah, good way to end the week.
Of course. Thank you so much for taking the time to present for us. We really appreciate it. Bye, everyone. Have a great weekend.
Okay. So I
Yeah.
think that we're still on. Chris, could you make me co-host like with the second user? I just had like a problem with my one computer, so I had to sign from another one.
Yeah, so I had a question about kind of going from ROS 1 to ROS 2, and it has to do with like when I was building our gazebo sim, I was noticing little warts in like ROS 1 and gazebo, and then I was fixing them and then sending like pull requests to people, and I was wondering if the people that really matter or care about it are actually working in ROS 2 and don't want to pull requests from like ROS 1 Noetic. Because some of them are
what kinds of like what parts, like gazebo core stuff, or
not core stuff actually. No, it was more like plugins. I think one of them was I wanted to create a gazebo plugin that acted like a POSMV that would have both a GPS and IMU that had synchronized timestamps. So I created like a what did I call it, a motion reference, one that combined both sensors and make sure that the ROS messages all have the same timestamp, because we kind of expect that in our real boat from our POSMV. And I sent a pull request to, I think, what's the name of the package? Like ROS Gazebo plugins or something like that. And
oh yeah. So that probably is true. Like, I mean, that's probably I think there's very limited, like for the plugins part, like that's much more like a community support. So you know, I guess my advice, intuition is that, you know, that would be something other people would use, especially in our community. But you'd probably have to host it and maintain it yourself. Like they're gonna, you know, that's kind of out of scope for them to like take on a new feature. And yeah, you know, they want to do stuff that is totally foundational, like IMU, GPS, camera. That's it. Yeah. So if it's more specific stuff, like we've done something kind of similar with like I don't know if you guys use any of them on their ASVs, but like you know, we use these like GPS aided IMUs, like MicroStrain or XSense or some of these, you know, they're pretty inexpensive. They're you know, two orders of magnitude less expensive than a POSMV, but they'll give you a final navigation solution. And so we've got a way to do that, you know, so that we've, you know, used in a bunch of different projects, and it's out there. But the key thing, like I found that the key thing to getting engagement is writing the tutorials. Like if you'll take the time to write a tutorial, so that when you know, the woman that was just on, her name was May Win. When May Win's graduate students Google, like, how do I simulate a POSMV, you know, the search engine will find you. And then, you know, and then I have found, I'll say also, I have found that the extra work of like helping folks use the software has been a net positive for us, in that, you know, yeah, we'll help students to a limited extent, right? Like, you know, we're not going to help students just say it doesn't work, can you help me? But, you know, if it's a reasonable issue request or something, we found that investing that time in the support and maintenance has paid. Like, we've had people do really significant contributions from the community of like, you know, here's a new feature, and like, wow, like I didn't know how to do that. That's awesome. So, yeah. So if, you know, and the other thing you have to, you know, I mean, I'm sure you do this too, right? You get on the GitHub page for something you're interested in, and first thing you check is like, you know, is it being actively maintained? Are issues, you know, being not addressed, but at least commented on, right? And, you know, or is it just kind of, you know, here I love this. I think it's an XKCD. It was at the end of because a lot of, you know, a lot of this world of open source software and stuff here, can I still share my screen? Can you see that XKCD there?
Yes.
Yeah.
Yes.
Is this right here, right? I love this, right? Like, you know, there's always this little piece.
Yeah.
You know, replace random person with graduate student, right? Some graduate student who long ago, went to work in investment banking, wrote a little piece of robotics code that is critical to your infrastructure.
Mhm.
So
That's great.
You glazed over a slide. I think you skipped it because you're running out of time, about DevOps, and I was wondering what was on it.
Yeah, here I can show that. Am I still sharing my screen? No. So it's just kind of like these were, I skipped over a few here. So one is, one of the things that we did, this was actually, we had an intern that worked on it last summer, which I thought was a really cool thing. Was this is from Ropos, but you guys are probably familiar with like connecting ODI connectors underwater, and so we did the same thing. There's a little video here of generated this mechanical model, and then have a plugin that actually is inspired by the ROV operator's manual, which says like, the alignment of these two connectors needs to be, within 10 degrees or 10 millimeters, in translation and orientation. And then it specifies the mate and demate forces. And so we were able to write a plugin to reproduce that, which was, I don't know, kind of a cool feature, very specific to this underwater manipulation piece. But the DevOps that let's see where, so, we're still learning, as, mechanical engineers. We have been, we are by no means like disciplined about using unit tests on everything we do, but we are able to do simple stuff through the usual Bitbucket calls them pipelines. GitHub is actions, I think.
Yeah.
Being able to do simple stuff like we have a Docker build that runs every time there's a pull request, so that we can do a little bit of regression analysis. We have static checks for the style guide. Pretty simple stuff, but it's been kind of exciting. We've used Docker more and more as both for continuous integration, continuous development, but also just for development. So, I've been really impressed by being able to run Docker in an interactive way and have it have access to the GPU. Allows us, some of our projects are using, Ubuntu 18, Melodic, and Gazebo 9. And then we've got some projects that are Ubuntu 20, Noetic, and Gazebo 11. And with Docker, it's really simple to switch back and forth between environments, and have kind of a set development environment for each project. So yeah.
Ever do deployments on a Docker image?
So this is totally out of. So yes. So as you guys know from Vork, like that's all that submission is Docker based. And then we are right now working with Open Robotics on, have you heard of their Cloud Sim piece? So basically, so you guys know, right, to run this software, the first step is to buy a dedicated Linux machine, install the right operating system with the GPU, so for students, that's a huge barrier. Right. And so to just try it out, if you're not familiar with that, right. And I tell the story of like, I got a new desktop a few years ago and I was like, all right, let me start working on it. It was like, it had like Ubuntu 19 on it and nothing would work, in the ROS ecosystem. So first step, reinstall the operating system. And not everybody loves to do that. The other sort of story is, we've done tutorials. We did one down in San Diego. We did one in Sydney, where we're showing students how to use this. And now in COVID, we're teaching classes using not the maritime stuff, but just using this infrastructure. And it takes dedicated hardware. And that is a huge limitation. So Udacity has a really good, slick, like almost single click, run your whole Linux desktop in a browser with GPU support. And so we're working with one of our ongoing projects with Open Robotics is, and I'm going to start teaching a class on Monday that's going to use, it is a really pretty rudimentary system at this point. It uses no VNC. The students have to like send these cryptic RESTful API calls through with curl to like set up a server on AWS, and then you get like a minimal LXQT desktop, but it's got a GPU. It's already got ROS and Gazebo installed, and so you can imagine you could, if you were an undergraduate student and you wanted to participate in Vork, you could do your development in that purely web-based environment on a Windows machine or a Mac or whatever, without installing anything on your host. And so that's all Docker image-based stuff. So yeah, I'm by no means I can use Docker, but I guess the one thing, if you're using it for development, Tully Foote has a project called Rocker, which is really pretty great because it allows you to like launch it allows you to take a Docker image and it overlays like access to the X server, access to the GPU, user privileges, mounts your home directory, all this, so it's pretty, I can, it's pretty slick.
Yeah, everything I've learned about Docker, I learned during Vork because I had just upgraded my machine to 2004, and then Vork was all happening in 1804.
Right,
so,
right.
But it worked great. It worked great, and I'm using Docker now to do the continuous integration of at least compiling our code to make sure that I have all our dependencies, because you're working on your machine that you've installed
has everything, right?
You deploy it, and so that's been great so far. But I'd like to know what the next step in CI to do testing that everything works, like how to approach that is kind of, it's a bit daunting.
Yeah, that's definitely like getting beyond just hey, it compiles and you've got dependency checks. Like that's where we're at. But if you wanted to do like real, like, all right, hey, we want to like put the simulation through its paces. That's tricky because it's almost like you're constantly developing features. So that would be sort of, you'd be writing the tests as you write the software. But I'll say that the low hanging fruit for us has been we've had much less issues. Like it's just so nice to have that stuff check your code and make sure you didn't introduce a dependency. It saves us a lot of time, even on small teams.
Yeah.
Brian, in the work that you were doing with I'm not sure who actually, but it's related to the question I asked early on about tiled bathymetry that was getting loaded in. Like we've talked about how we might do that, but it seemed to me, maybe thinking about it naively, that the way to do it is really outside of Gazebo, and that you build an engine that loads tiled bathymetry in and serves it up to a sensor that maybe then is running in a plugin in Gazebo, or it doesn't even have to be that actually. All the sensor needs to know is, well, yeah, it would mean that the whole surface, the whole DTM would live outside of Gazebo and would not be in Gazebo, and would just serve it up into Gazebo maybe for visualization purposes in a tiled way. But I'm not sure that's
collision detection, right?
Sorry, say that again, Roland.
Like collision detection for like AUVs, you probably want for that. So
yeah, that's right. That's right.
Yeah, and I think there are parts of I'll give you the link here. This it's really just a demo, but it shows, let's see, it shows the plugin. I'll put it in chat, or I can just email it to you. It's part of this Dave project. So and again, it was working with Mike Jakuba and others. And we do have some pre-processed bathymetry data you can try it out with. It's in the repository, but it does serve it up within Gazebo, and that's kind of, I could definitely see like doing, like you said, like doing it completely outside of Gazebo. I think that you know, I guess the philosophy there is that, and probably bathymetry is a case where you could do it either way. But, you know, if you've got something else that, you know, imagine like the subterranean challenge where you're doing this in a very large underground cave environment. You don't you know, we're, as the developer, not doing both the environment generation and the sensor development, you know, so because there you've got a cave wall and you want to be able to look at it with a camera, with a LiDAR, and with a sonar. And so we might be just doing the sonar, but we want to leverage the LiDAR piece and the camera piece that's already there.
Yeah.
Right. So it's a little different use case. So I think that's kind of how we ended up there. But yeah, you could do it, probably do it outside. So I don't know, are you guys interested in all? Is there anybody at UNH that would feel that, you know, and again, I'm not biased, but I am biased, but there's no conflict. It would be cool to have UNH have a Robot X team. I think ONR would help you guys buy a boat, maybe.
I think that would be really cool, but I'm not sure I'm the one who decides.
I feel like we have our own, I mean, so we took a different, it's interesting because we took a different strategy when we first started getting into ASV work, and that is that we figured we would just go fumble around in the field and operate out in the field and as frequently as we could and figure out all the things that we needed to fix. And you know, and when there was a problem to fix, we would fix that and then move on to the next thing and just iterate as quickly as we could and go back out into the field as quickly as we could. And so for better or worse, that's kind of what we've done. So we've been really late to the simulation game in some ways, and I'm probably paid for it in some ways in doing that. The way we're doing it is we have the luxury of having our own boat, having you know, peer facility and support and all that stuff. So we can go out and do that. You know, we don't have to deploy on a big ship for $20,000 a day to go and do those tests. So all of that's to say, we have a dance card that's so long for field operations. It's really hard to find time to jump into one of those competitions as much as I would love to. Like, we learned so much. We learned more in those like 2 weeks of diving in than I feel like we had in the last year in many ways. So I definitely see the value of it for sure.
Right. I think the only, you know, maybe the only added value for, you know, for you guys is that I mean, I don't know how much, I don't know how much it almost like forces students to get involved, right? Because traditionally, like, they become part of like a senior design, and, you know, and then you just, you know, and I don't know how UNH does it, but, you know, we've seen a lot of the teams that, you know, it just kind of brings some resources to it. But it's also like, I was always kind of at University of Hawaii, I was kind of, I think it looked in a much smaller way, kind of in the same outlook as you have, Val, of like, we've got so much to do that's real science. Why would we need a competition to, you know, create these sort of, not fake, but, you know, contrived things, right? Like, we have to actually go do this, you know? So, you know, and so that, you know, we were always pretty successful in getting folks involved that way.
Well, if I may add, also, I totally share your perspective on things. I think that Maywin Thane might be a good person to approach to regarding this, because she's the professor of the mechanical engineering, and she runs the RV and the ASV teams at UNH. Personally, I tried to kind of build a team and Robot X team a couple of years ago, but honestly, like, everyone, we're pretty much busy with their own
That's great.
projects and stuff. So it didn't really go anywhere. But yeah, I think that Maywin might be.
I think Coral brings up a really good point, and it's a sort of a systemic problem that we have as an institution, it seems to me, and that is that we pile so much on our students that they feel like they barely have their head above water, and we need to find a way to, like, invest in the ability for them to break out of that and actually participate in something like this for all the obvious reasons.
I approached to different grad students, and, you know, when if you're not under a strict program that kind of relates your research to it, then it's kind of hard to
Yeah, definitely.
But I mean, Mayween has those two teams that she runs, and they participate in MATE or other programs. She's also involved with the Navy as well, and so I think that through her, like maybe build a program, Robot X program at UNH, that might be an option. Personally, I'm obviously interested in that, but I mean,
I think I kind of the piling on to students, I think is, you know, it has to count for something beyond just, you know, I've seen a few cases, and I'm always surprised of like student-led teams where it's sort of just student interest and passion. And I always ask like, why, you know, not to be too direct, but like, why are you doing this? And, you know, and it's usually like, well, like I know some of our international teams are like, this is a huge resume builder for them.
Yeah.
Right.
But as being as part of CCOM, I do enjoy the privilege of, you know, having the resources both on the software and hardware side. So, I mean, I have like small Z-boat boat that is available for field experiments like here. And then I also have, now I have the simulation that you guys developed since December in our effort in work. And so
I think the ways it can be integrated is like through senior design, right? And some schools, like, you know, the schools that we see be successful at that, like actually where I went to school now has this, like, you know, at University of Missouri, Rolla has, you know, they've got this pipeline. They don't really do this kind of stuff because they're in the middle of the country. They do like SAE formula and this, like they get people involved when they're freshmen, right? And they have like design, and they're getting class credit for it, right? And so, you know, so that's the way we did it at University of Hawaii. It was through like their senior design, and we had a program where juniors could get involved. So they have to, you know, students are super busy, so they got to get, you know, I think credit's the easiest thing to give away.
Well, I think that also a key point is that you would want to have an interest in having students involved and developed in this field. If you're focused more on operations side and stuff like that, then it's like what you mentioned earlier. So you have like things on the operational side, then like you have things more on the academic side, and so I think there is this balance or conflict.
Right. All right.
Yeah.
Brian, I'm gonna sign off.
Yeah.
It's certainly great talking to you, and we'll chat some more.
Yeah, we should keep talking. And I know that some of the folks will probably be up your way. I think I can't remember the dates, but I think in May. So
great. Yeah, we'd love to have them.
All right.
Thank you so much, Brian.
All right. Talk to you soon.
Bye.